and then give the operating system a chance to see who should be on that CPU, also referred to as time slicing. So we have major and minor clock cycles. A major clock cycle is once every second, just like on Unicos and on Crays. And every major cycle we have an opportunity to reorder our run queue and to evaluate priorities. Our minor clock cycle occurs 100 times per second. In source code it's known as Hertz, HZ, the Hertz of the system. And that occurs 100 times a second, referred to as a clock tick or a minor clock cycle. And basically during that minor clock cycle the kernel can do some process accounting. It says here there's a 10 millisecond charge to connected processes, basically the amount of overhead it takes. No, I'm sorry. What it's saying there is that the process is going to get charged for 10 milliseconds of usage. Okay, and if you've exceeded your time slice, you would then get kicked out. And we're going to come back to this a little bit later. Basically, there's a parameter called slice size that says how many minor clock cycles do I get before I'm preempted. Okay. So every 10 milliseconds, I go into a counting area, I look at global memory, I do a few other things. I also charge to each process 10 milliseconds of time. And this is something different from Crays, I might point out. In Crays, we actually count and instrument on our exchanges. So every time I go into the kernel in Unicos, I've got a counter that I maintain in my process table, PWS table. In Irix, we don't instrument those hot paths because of the real-time market. Okay, every millisecond that they can save is important. So instead, it's more of a polling. I periodically check to see what is used, rather than saying, here's what you actually used and counting it on exchanges. So during the minor clock cycle, we're going to select the process most eligible to execute on the run queue and do other housekeeping tasks, such as check for memory shortage and a few other things. And in fact, when you get these clock interrupts, there is a module called clock.c that you're executing. And clock.c is the most common thread that you're going through to do this sort of maintenance. Yeah, here it is. Hertz is defined as 100 typically. Housekeeping work, the monitor work can be done across all CPUs, but there is a master CPU, CPU 0, that does most of the clocking type of work. You can move it to a different CPU. There's a command called mpadmin that allows you to move your clocking CPU off to a different number. Okay. And it looks like that's the end of that section. Check our time, we're at 11. I was going to go until 12. What time do you want to? I typically go 12 to 1 for lunch. Is that acceptable with everyone? Or 11:30 to 12:30, I don't know what you like, but I'd rather go 12 to 1 right now. And I figure about 5 o'clock get finished. The next section then is on memory management. Are we doing okay? Not too many questions right now.
I think you were doing okay right before 5 o'clock.
Okay. Well, we can work out something there too. Are we going through this too quick? I'm assuming that a lot of it's basic for a lot of the people I see in the class. So I tell people you got to slow me down by asking me questions. So that was a little bit of overview of the software. The next section is on memory management. And again, this is just trying to repeat that we've got a shared memory concept here. We've got router technologies with multiple paths to get between one CPU and another. In this particular example, CPUs in router 0 or router 1 have 3 different ways negotiated here to get to router 6 and the data that's sitting there. So it's a single large shared address space, but it's physically dispersed amongst several nodes. Former systems were common memory type of systems, uniform memory systems, Cray 1, stuff like that. The T3D, T3E was the first direction where Cray went into non-uniform memory architectures. And again, former systems were accessible over a single bus, but now we have this interconnection fabric. For SGI people, they use that term, but for Cray people, we've been calling these routers for 20, 30 years. So it's not new to us, it's just the way it's been put together in the packaging. So to a processor, main memory appears as a single addressable space containing blocks or pages. When we reference things in memory, it's referenced with a page number and then the byte offset into the page. So whenever I go off to memory, I'm referencing a whole page. And everything that's being looked up in the TLB buffer is a page reference. And then off of that TLB, you've got the page number and then the byte offset into the page of what you want. So it's not a byte machine, it's not a word machine, it moves things in pages. And then this concept of page migration being used to reduce latency. And then the concept of hierarchy, where we're trying to keep everything in our process registers, but that's not possible since there's only 64 of them. Then we try to keep things in a 32 KB cache if we can. Oracle database transactions on credit cards would fit into a 32 KB data cache type of thing. The amount of data associated with my credit card transaction isn't more than 500, 600 bytes of data. Then we've got secondary, then we've got local memory, then we've got remote memory, and possibly data that's in remote cache, such that if some other CPU changes a variable that I'm using as well, I may actually have to go all the way to their cache to synchronize with what their data is. And we're going to talk a little bit about that, called false cache sharing. For example, an application may have a global write counter, index counter, in the same groupings of the program as a whole bunch of read variables. And then every time I write that write index counter, I'm going to invalidate all the read variables on that cache line. And that's very expensive. That's called false cache sharing. And so we end up starting to worry about cache line geometries. Instead of how things fit into our bank geometries and our vector register sizes, we worry about that cache line. And whenever I manipulate stuff, it's at a cache line level. So we get into padding, where we'll put in some blank dummy variables to make sure the global reads fall into the next cache line. And then the only thing on that cache line would be the write variable. And then every time I modify that write, I don't invalidate all these reads and slow down all the CPUs on the system. But that's called false cache sharing. And it's more of a common problem in multi-threaded environments where you have multiple threads. They're sharing the same data array and sharing the same global variables, for example. So we got a nice little picture here just showing the hierarchy where we're sitting here off with our CPU. And our CPU has the functional units and registers in a big brown ball here. We've got the TLB buffer, which is doing our virtual address to mapping it to physical addresses. And if I can't find it in the TLB, I ask the operating system to put it in there for me. By the way, the kernel address is always what's called hardwired into the TLB. Hardwiring the TLB means that nobody else can preempt that. So the kernel entry points are actually hardwired in there. Now that's not a real hardwire, it's just terminology going back to old days when we did hardwire things. But it is a software load, a permanent load of that TLB address. And then just showing primary cache, secondary cache, and then if I have to go to secondary cache, I may have to go off onto a sysadd bus. This is the system bus here is that sysadd bus, and it's shared between two CPUs. Now in the future architectures, they're going to start adding more and more CPUs onto that sysadd bus, which means it's even more critical that we keep stuff in secondary cache and not have that sysadd bus busy. As we add more and more CPUs onto the bus, we get a new bottleneck. And then off on a hub chip, and if our data is off on the I/O, we go to that crossbow board. If it's local memory, we go to the hub chip to our local memory, or if it's remote memory, then we have to go across the topology through various routers to another hub chip to get to their remote memory off on the topology, off on the system somewhere else. And a lot of this I think I've described. Again, the addresses are mapped from virtual to physical through this TLB buffer. That's the concept we do not have in a Cray typical architecture. We're a real memory machine. Real addresses are built into the binary relative to some sort of addressing schemes. Nowadays we call them logical address translations, LATs, on the T90, for example. Somebody asked me to compare to T3Es as well. I did not spend much time in T3Es, so I can't add in there. Let's see. I'm just seeing if anything else in here. The hub chip knows where the areas of memory have been assigned to the nodes and which area of memory has been assigned as local to this node. and then the hub acts as a switch to direct the request either to the local memory or to the remote memory. And when the hub chip recognizes the local memory does not contain the data, the address goes out across the interconnect fabric through the routers to another memory module.
In T3, it's very much the same. They do it on a C chip, which sits next to the CPU. And all references start off as global virtual addresses.
Yeah.
C chip, then it goes into lookup table, translates it into.
Now in the T3D, we didn't have much of it. Each CPU was not getting to other CPUs' memories. The newer T3s do get into this, but also the caches were typically smaller on the T3E, making cache coherency not as critical. And I understand the latest T3E does have a lot more hardware support for cache coherency than the prior T3Es. But again, what's the size of the cache on the newer T3Es?
It's not so much cache coherency as streaming.
Okay, which is the opposite of cache coherency. Streaming being I'm not reusing the data, but I got to push it through this cache mechanism. Okay. Let's see. So in this section, we're going to talk about how memory a process resides in memory. We're talking about this concept that we've got the kernel, and it's going to keep referring to this concept of a swapper or SCED. We have that in Unicode, but in Irix it does nothing. Irix removed all the swapping mechanism from standard Unix. That Cray went in the direction of NSCED-V, Irix went in the direction of removing it. There is no memory scheduler within Irix. And for this reason, I tell traditional Cray customers, do not oversubscribe memory like you did on a Cray. It's not uncommon for me to find workloads 20 times the physical memory on the system. On an Irix-based system, there's no political scheduler for that. Everybody's going to get hit. And I tell people, when you're tuning an Irix box, the first rule is don't oversubscribe it. Do not swap to disk. Don't have more processes on your run queue than you have CPUs. And don't use all your file system buffers. And we're going to get into some of that stuff. So the swapper or scheduler really does nothing in Irix. It has major impact in Unicode. And when I'm tuning Unicode systems, I got to tune that swapper first to get things into memory so that I can tune my CPU stuff. On an Irix system, everything's always in memory. There's always something there, so I got to worry about memory scheduling last and worry about CPU issues first. And the biggest thing is, again, locking things down into caches so that they are uninterrupted. Okay. So historically, this thing called swapper, if I started running short of memory, would swap the entire process out to the swap device. On a virtual memory machine, there are some advantages. A Cray is traditionally not a virtual memory machine. Virtual memory machine allows the programmer to ignore the physical layout of the machine, and everything is done in virtual addresses, and the operating system converts it into physical. So some of the concepts here, again, it gives the illusion that there's more memory available than physically installed on the system. And this is more useful in applications that don't use all their memory. Again, the sparse matrix solvers, gather, scatter type of routines, Monte Carlo algorithms, chemistry codes, things like that that are randomly striding through data that's sparsely populated. And then there's nothing in between.
So what is a Monte Carlo?
That's something used in the physics area. It's what the gather, scatter hardware in the Cray world was designed for, was to make this Monte Carlo algorithm go quicker. But it's a physics algorithm. Lionel runs it quite a bit. It's science. But that's why we implemented gather scatter within the Cray architecture, was to do those sorts of algorithms more quickly rather than sequential strides through data. But the thing here now is that there's parts of the array there's nothing there. It's been zeroed out to zero, but I don't use it. On a Cray, I would be wasting that memory. On an Irix machine, I can take advantage of that memory because I'm not really using it, so it can get pushed out to swap, and then I can use that memory for something that's actively holding real data. Okay, and I've got a program I play with what percentage of the array it actually uses, so I can build a 64 gigabyte process and only use 1% of that data. And then the other, on a Cray, all the other memory would be totally wasted. I could never take advantage of that memory space. And every time I swap the process, I'd be adding to the I/O load of moving this huge program that's not using all the physical space it asked for. Okay. So this allows the program to think that there's more memory than physically installed on the system because we've got this virtual addressing capability. And I'm going to talk a little bit about that as we go along. It allows me to run programs that are larger than my physical memory. The whole thing does not have to fit into my physical memory anymore. Whereas on a Cray, the entire process had to fit in memory. And the process does not have to be entirely in memory at once, only the pieces that I'm actively using. So a lot of this virtual memory concept is a memory efficiency question, allowing me to take advantage of all the memory that I have down to my page level granularity. If there's a page that I never use, I don't need it to take physical memory for me. And again, the translation mechanism to convert this is called the translation Lookaside buffer. And page tables are where we keep that information at the system level. So memory pages, it's a paging machine, and all memory references are at a page level. Based upon pages, all sizes are equal sized blocks, but it depends upon your system whether you're 4K or 16K. The workstations will be 4K, but the large origins will be 16K. And that makes sense. I would rather keep my small system in a small I/O nature, small memory nature, because of the types of programs I'm running. Whereas on the bigger systems, I'm running huge things. And I don't want to have to go off to memory every 16K byte if I've got a 64 gigabyte system. There is the capability on the Irix 6.5 of having larger page sizes on a per process basis. So if I've got one process that's huge in memory, I can say go to a larger page size of 16 megabyte. That is the largest page size you can represent in Irix. So I can go from 4K byte to 16 megabyte in page size with whole powers of 2 numbers. So if I've got a 64 gigabyte process and I'm missing pages every 16K byte, I'm going to take a lot of Tlb misses, and I'm going to be constantly asking the kernel, where's this page? By increasing my page size, I may not have to ask the kernel for as much information. I'm able to describe more real estate within that same address. But again, hopefully I'm striding through the data such that I use all the data on that page. If I don't use it, if I just pull 5 bytes off of it, now I'm moving 16 megabyte pages on the system, but my gather scatter routine is only going to a couple of bytes on that page. So it may hurt you if your program is randomly going through the data. Okay, so it's a matter of knowing how you stride through your data. And this is something that has to change between codes that were on vector Cray machines, where they were designed to stride through the data in vector chunks, vector register size chunks. Now we have to worry about that whole algorithm fitting into the geometry of a cache. And the way we stride is different on cache-based machines than on vector machines. So they're just saying here 1K byte powers of 2 is 1024, 1 meg, 1 gig. And then for a memory size, they're saying if it's a 64 memory size, the number of pages on the system, in this case, is 4 million pages. Now in 6.5, SAR capital R, oops, I'm not on 6.5, that's why. I've logged into a machine in Egan called Do, which is a customer service division machine. And SAR capital R will give you the breakout of all this. So in this system, I've got 131,000 pages of physical memory available to my users. My kernel's using 11, almost 12,000 pages. My user on this system is presently using almost 10,000 pages, or 100,000 pages almost. And then there's a breakout for my file system cache, for inode information, for delayed write data, the dirty data we were talking about, synchronous I/O, stuff it in the kernel, let the kernel do it for me. And then actual data that's being reused, and then free. And here's that bug on the system. My empty is wrapped and is larger than my physical memory. That is a bug that's showing up on this system right now. So watch for that. That bug I've opened up 6 times in the past 2 years because it keeps coming back. Because they derive a number and they occasionally go negative. That's what negative looks like on an Irix box when I wrap negative. And I was also surprised when I went from Crays to Irix, where with awk I'd get INF for infinity and stuff like that, where Crays would handle that sort of thing a little different. So number representation causes some effects. So on 6.5, SAR capital R will tell you exactly how many pages you have on your system configured. And here it was using a 64 KB page size, and then just figuring out how many pages on a 64 gig system, which is what Flurry is presently configured for, I think. And again, every time I reference one of these things, I basically reference a page number, and then there is a byte offset into that page. So whenever I go off to memory to get something, I don't get a word, I get a full page, 16 KB. There are banks on that node. You could have 4 or 8 banks. It'll make the page come faster. But I can't interleave pages. Only one can come in at a time. And as I mentioned earlier, sysconf page size, we'll print it out. This is a 4 KB system on your Indy, and the larger systems like Origin 2000s are a 16 KB page size. Okay, so sysconf will tell it. It's actually got 2 parameters there, page size and page underscore size. They'll be the same thing. Now your user process is broken into 3 basic pieces. Actually, they've got a 4 listed here as well. We've got the text portion. The text portion may be shared, for example, your login shell. If 15 people log into the same machine, they'll share the executable portion of that shell. This saves memory, but it also creates node conflicts. If that shell is sitting off on one node, 16 people now have to go to that node to get the page, to get the text, executable portion of the program. And the text portion is read-only. Nobody can modify a text portion. The second piece that's listed here is the data portion. This is where I actually save my variables and save my heap or blank common storage areas, so that when I'm asking for memory to put in data, all of it's going into this area. Okay. And there are 2 things within this data area. The variables are going to be at the top of the data portion, like index counters and things like that. And then I've got arrays, or what are called blank common storage, BSS space. Another name for it is called the heap. And the heap is at the end of this data portion. And the 2 are growing towards the center. Okay. And you've got limits for how big the data portion can be before you get killed. Data portion is read-write and is private. A process cannot touch another process's data portion. The third portion is called the stack, and the stack is for the operating system to keep track of where you were. Your program counter and all your local variables are saved on the stack, so I can jump off, do some other subroutine, and when I come back and exit out of the routine I jumped to, when I come back I can restore the environment I had before I did the jump. Okay, so there are going to be 2 stacks. There's one in user space and there's one in kernel space. So if I jump 15 routines deep in my program, I go main, routine 1, and keep going deeper, I'm actually going to have 15 frames on the stack to describe each of these subroutines. If I multi-thread, I'm going to have pieces of the stack for each thread. So as I multitask or multi-thread, my stack requirements are going to get larger. If I go 128 threads wide, 10 routines deep, that's going to be 1,280 stack frames sitting there on my stack. Okay. So the stack is private and it is read-write. The last piece that's marked here is shared memory, which was new in the T90 product line. The inter-process communication was called SHMEM. Now in the Cray world, there's another package called shared memory. That's different than this. It was a Unicos shared memory implementation rather than the standard System 5. We ripped out IPC as soon as we implemented Unix on Irix because of the IBA ILA. We were hard-coded into what we could address, and we could not do virtual addressing. Until we got to the T90 and LATs, that's when we've brought IPC back into Unicos. So the text portion is the executable, the data portion is my data, and then the stack is my subroutine information. And this is a virtual address space to the program at 0 to memory max. Assume that physical memory is addressable as the first byte located at 0, and then you've got byte offsets into the program. So you're going to generate machine code that's 0 based. And the compilers are going to generate program addresses for a virtual address space within a given address range. So still, as far as the program is going to be concerned, a physical contiguous addressing scheme and contiguous addressing space. The operating system is what's going to determine where it actually exists in memory. Again, the compiler doesn't need to know where it exists in memory. It will later load the program, and at execution time, things will be figured out. And here we're just trying to show that when we reference an address, the virtual address has the page number and then the byte offset into the page. And they're showing a process here where we've got multiple pages and the page numbering going from 0 to 9. And then trying to map that into a virtual address space. And Irix is all hex-based. And this is assuming a 4K byte or 1K hex addressing scheme. I don't see anything more. Down at the bottom basically says the rightmost bits are the address or the byte offset into the page. Depending upon whether I'm 4 or 16K byte page sizes. So here we're trying to look at this. This is a per process page table. Every process has a page table entry. This is maintained by the kernel. When we were looking at GMEM usage when I did that zap, we were basically looking at the contents of the page table. And in the page table then it's got the page number, the virtual, and then the physical page number where it physically resides out on the system. Okay. And there's going to be a valid bit in there that says whether the page is valid. I could reference a page that is not valid yet. We don't create pages until we reference them. So I could malloc and ask for memory, but if I never touch it, I never allocate that memory space. We'll talk a little bit about that as we go along. So the valid bit says that the page had already been referenced once. And then the page could be in memory, could be in cache, or it could be out on the disk drive. And that bit's going to describe where it is. If the valid bit's not set, then I have to create the page, and the block transfer engine is used to basically create that page. So the page table is basically what the kernel uses to keep track of the mapping of virtual to physical. And it's also called a PTE, a page table entry. The PTEs, that's what we're looking at here. So the translation lookaside buffer is what keeps track of the subset of these page tables. We can hold 64 addresses in our TLB. And then if I reference an address, if it's not in the TLB, I ask the kernel to say, go to your page table, find the page, and then put it into my TLB for me. So the translation lookaside buffer contains both the virtual page number and the physical page number. And there are different sizes. This is showing some of the different sizes for the different chips out there. This is the number of TLB entries, but the way it's being used by the software, there's 2 entries being used together for 2 consecutive pages. So really you only get 48 or something, 100, half of these, and 64 of the R10K that are actually being used. I don't know why they're not upping it more. Again, this is real estate within the chips area type of thing. And I haven't seen that there was going to be an increase in the R12K. I don't remember for sure. But I haven't seen much change in this area in terms of, like the R8K can handle a lot more TLB entries within the chip. Okay, anyway, don't see anything else of interest on that page. And by the way, TLB misses are counted in the hardware. So you can see how many times a program actually missed its page and possibly tune the application to reduce your TLB misses. This is trying to show that we actually reference 2 pages at once. So in our TLB entry, we're showing the virtual and physical pages, but it's mapping two adjacent pages at the same time. And that's why I cut the 128 to 64 entries. And I'm not sure why it does that. The assumption being that I may as well load two pages in at the same time. But it seems to me there'd be other ways of doing that. So the TLB address contains the virtual page number, it contains the physical page number, and then it's got what's called the address space ID. And the address space ID is basically describing which node this particular page is on. There's also called the NAS, node ASID, address space ID. So whenever I reference something on my chip, I've got this TLB Lookaside buffer. If I can't find it in there, I have to fill the TLB buffer from a page table entry, and it's the page table entry that pointed to the actual location of the process in memory. Ideally, the TLB we'd like it to be large enough to hold an entry to translate every possible virtual address. However, large TLBs are not practical. They can only hold a subset of the page table. No matter what you do on this paging system, the page table is going to be bigger than whatever real estate you have on the chip. Okay. And again, it maps to two adjacent pages. When the virtual address request in the CPU falls within a range described by the address in the TLB, it's able to supply it immediately. If not, then it's going to get that's called a hit. If it can't find it in the TLB, it's called a miss. And we actually take an interrupt into the operating system to handle misses.
So
Go ahead.
ask about this page here.
Go ahead.
It says page X, for example, on your virtual page X. And if you come across, I'm looking at some other page, 13.
Okay, I'll go one more back for you.
So it says virtual page X, and it translates to some physical address.
Right.
And because these pages are 16K bytes, right, is the adjacent page, the second virtual page entry, is that 16K beyond the beginning of the previous page?
Yeah, by default, but again, we can change these
Right.
default page sizes.
Okay.
Anything else? So this was just showing the same sort of concept. We've got this user process sitting out there with the text portion, the data portion, and the stack. This one happened to have taken 10 pages. So it's like 16 kbyte per page times 10. So we've got 160 kbyte total size of the process. That's a realistic page size for a typical Unix process. By the way, the PS command will show you the number of pages. So I did a PS-L, and my shell is 99 pages of virtual size. Okay, and this is a 4 kbyte system. So 99 4 kbyte. But actually sitting in memory is 74. And the difference between 74 and 99 is memory space I've asked for that I'm not using. So in a virtual memory machine, I could free up, what do we got there, 19, 23 pages, something like that could have been used by some other process that were being wasted. So PS-L shows you the actual size of your process. And then GMEM usage showed how it was split out, gave you this kind of mapping. And note that it's got some pages in here. For example, in this data, they've got a page that's marked invalid. That's a page that's never been referenced, and there's no physical mapping to physical memory for that page. If I reference the page, the kernel's going to say, oh, it's invalid, so therefore it will create the page. But you won't create the page until you actually reference it. So when the process is loaded into memory, the kernel establishes a page table for the process, and each virtual page will have an entry in the page table. If a particular page resides in physical memory, the page table will be marked as valid. Otherwise, it's marked as invalid. And then the task of translating these virtual addresses is what happens in the TLB. All I do when I can't find it in the TLB is tell the kernel, look up in the page table for the physical address and stuff it into my TLB buffer for me. So if the CPU does not find a match in the desired page, then the kernel must get involved and load an entry with the appropriate page table contents, and then reissue the affected instruction. And note also that the physical pages could be scattered all over in the system. They don't necessarily have to be physically contiguous in terms of their physical page numbering scheme. And I guess they're just saying purpose of page memory gives them a greater flexibility in using that physical memory. I don't have to waste as much. Now, there are several issues here. I've got to talk, we've talked about virtual memory concepts. That's what the TLB is mapping virtual to physical. But then the second piece of this is what's called demand paging. And demand paging says, I don't worry about the page until I demand it, until I need it. And this is where we can save memory space again. If I keep asking for memory but never actually use it, demand paging says, reserve the memory for them, but don't create the page and don't consume memory for it yet. And then the ones that actually need memory can use it, and the ones that are not using it, are not demanding that memory, don't have to use those. And again, a sparse matrix solver is an example of this, or database engines, where they may be asking for memory and they don't use the entire space of that memory image. So when a process is created, only a small amount of memory is initially initialized or consumed or zeroed out. And some memory is needed by the kernel to control and manage each process. The kernel uses what's called the kernel heap to keep track of information on these processes. And the code and the text portion and the data portions associated with the process remain in the file containing the program which is being executed. And by the way, a lot of these executables can sit there in file system buffer cache, and you don't have to go to disk to get them. Therefore, when a process starts, a newly created process, most of the pages will be marked as invalid, and then as I reference the pages, they'll go from invalid to valid. And then the creation of the page would have to occur if it was an invalid page that I just referenced, for example, has zeroed out the array. So pages are created and allocated only when they're referenced. I could ask for it and never reference it. That won't consume memory. There's a reservation and then there's an allocation. Those are two different levels. We should probably save that. And a lot of that stuff is not working very well in 6.5 because of Miser. Because Miser reserves memory too. By the way, it doesn't really lay this out in here, but in older Irixes you could have swap less than physical memory. Whereas in Craze, we always had it at least at physical memory or larger, whatever the memory subscription ratio was. We needed complete backing store. In 6.4, you didn't have to do that. But in 6.5, because of this reservation mechanism, you have to start doing that now. I advise people to have a one-to-one swap to physical memory. And it's not written in the documentation anywhere, but it is a requirement. And I just got to save some of that until we get back into Miser. And with memory and swapping, there are two levels. There's the reservation and then there's the allocation. And I can reserve space on swap but never use it. But if I actually reference the page, it moves it from a reservation to an allocation. The application knows nothing about this. This is simply the way the operating system manages its memory space.
So that's why you could request it and never use it? Why a process could request it and never use it?
Yeah, for example, in the stack, I could ask for memory, but then not have to do the subroutine calls. I could have a larger stack page size and not use all that memory. I could ask for, one thing they do, a lot of this goes back to Fortran. One thing they do commonly in Fortran is ask for this big blank array space, but then they carve out what they want into their individual pieces. Okay, so I may ask for this big huge space and not use all of it just because of the way I manage my memory space. And a lot of this goes back to older memory management algorithms where we had what were called heaps and stuff like that that could grow and shrink as I needed memory and stuff. So there are a lot of reasons why a program, there's always going to be some wasted space. And a program may not need that space for whatever reason. Okay. So demand paging gives me better memory efficiency. The stuff that's sitting in memory is hopefully actively being used. If I start oversubscribing memory, only the stuff that isn't being used would get pushed out. Whereas on a Cray, the entire process would get swapped out, and that impacts the performance of that individual process. What really matters in an Irix system is if I reference a page and have to read it in from swap, That's what matters, because that's going to show up in my wait times. I'm going to have to wait for that page to get loaded in. Let's see. And basically, the set of pages is actively using is called the working set. So you may have a virtual size that's bigger than the working set of what you actually need to work with. One of the problems in this area, though, is traditionally in the compute market, we zero out that array before we use it, which creates a reference, which creates an allocation. But then we can push that allocated space out to swap and never reference it, and that doesn't hurt me, as long as I don't have to go back to the page that I zeroed out. But a lot of these applications in the Fortran world will zero out their array before they use it. Whereas in C programs, I may just malloc, not necessarily use it. Okay. When I do take a page fault says I cannot find the page address in my translation Lookaside buffer, then I have to go to the kernel, and the kernel will put me to sleep until it can find the page. And by the way, the page table may not be in the kernel's TLB buffer either. So the program could take a page fault to find the data. The kernel has to take a page fault to find the page table. So you could have multiple page faults in order to actually satisfy the page miss. So the procedure for loading a page, the process references a page address. The CPU attempts to translate it in the TLB. We assume that no entry in the TLB can translate it to a physical address. The virtual address is not in that TLB buffer. So we take a software exception to the kernel, what's called a validity fault, and the current running process is suspended until that fault is generated. And by the way, this is a hot path that is not instrumented. You can't see this hot path with system time and things like that, because it happens all the time. They don't want to put in counters in that path. They don't want to have to count this too much. So when I take a miss, it's called a TLB miss. It passes control to the Irix kernel. It's also called a validity fault. The kernel exception handler, interrupt handler, searches the process page table for a valid entry. If none is found, if a page is found, the entry is placed in the TLB and the instructions reissued. If it's not found, then we've got to create the page, allocate the space, create the page, and then supply it. If the kernel's exception handler cannot find a matching entry, then the desired page is not residing in memory. It will then locate a free page in physical memory and associate it to the current process by adding an entry to the process's page table. The kernel then initiates an input operation to fetch the requested data from the file system when the executable program resides, or if it's data, we have to go to the swap device to get to the data. The process is put to sleep, allowing other processes to run while we wait for this transaction to finish. And then after it's back, it is woken up and rescheduled. So we're just trying to show here that we've got this user, all the pages are mapped in a page table on a per process basis. Some of that real estate is in our TLB buffer pointing off to physical memory, but the stuff in physical memory is either residing out on the swap device as data or as the executable portion that resides in the file system. When I've got a shell, I don't put anything out, any executables, they don't go out to swap because they reside on the file system. I just invalidate the page, and then I can read the new page in later when I need the executable portion. So some of the advantages: it frees processes from size limitations. It's transparent to user programs. You don't worry about it in terms of the management of memory. And it has the ability to allow more processes to fit simultaneously into the same memory as a swapping system, because you're not going to waste all the memory image for space that you may not be used. Disadvantages: I have to wait for the page when it's being loaded. The extended accounting data tracks how long I wait for the page. And during initial stages of a process, when I'm starting it up, I may generate a whole lot of page faults to create the pages for the first time. Now they've changed that behavior a little bit in 6.5. In 6.4, it took me 10 minutes to grow this 1 2 gigabyte process. Now I can get it done in about 20 seconds. But they've changed the way they are implementing this, and hopefully we'll see a slide that covers some of that. Now there's also something called quick starting a process, and the RQS is what makes these objects quick start or have quicker startup times in terms of initiating the pages.
Is this what happens after you,
After you do an inst, there's going to be an RQS done.
so that's what they're doing, is they're taking that image and they're making a quick start of it?
Essentially, I haven't dug in at RQS other than what's on this page and stuff. But yeah, you get that RQS when you're done with inst, which is basically everything that you've put in is now going to have some attribute information built into it to make the initialization go quicker. But the details of that I don't know anything about.
Kind of an in-joke, because it takes so long to run the RQS process.
Yeah, well, there are a lot of things that can get slow.
And then are you ready to make it quicker?
Now, when memory starts running short, I have then what's called page stealing. So page demand is what's creating the pages as we need them and referencing them. But when I start running short of memory, there's a process called vhand. And vhand is a user daemon space. It's shown with PS in 6.2. But 6.5 is actually a kernel thread. It's been moved into the kernel. So vhand's job is to recognize that there's a shortage of memory and start stealing pages away from processes. And basically it's going to put it into the file system buffer cache and let the kernel worry about it. Vhand is passing the buck. It's basically saying, I got a memory shortage problem, so it shoves it into cache, turning it into an I/O problem. And it's up to the kernel to actually push that cache down and push the data out to the swap device itself. And we're going to talk a little bit about that. But page stealing is basically kicked in when I run short of memory. I don't steal pages until I actually have a memory shortage problem. Let me see what I've got here in my system. sar-p will give me that page steals. Right now, I had 72 pages when I started, but then there was 2 pages and no pages, giving me an average of about 19 pages. But this could have been just SAR itself creating the pages that I needed, and some of them got stolen. We're going to come back. There's hand samples in the workbook of sar-p. Vfault is when I actually miss a page. So that's my Tlb miss. And then where do I satisfy it from? dfill says I created the page for the first time. Cache per second says I found it in cache. pswap says I had to go to the swap device to get my data page. Or pfile says I had to go to the file system to get my executable page. And what we were looking at here was there were 72 pages stolen from this process as it created them. There were 86 pages faulted, 67 of them were created, and then in the process I ran short of memory, so I had to steal 72 pages. And I stuffed them in file system buffer cache. And I actually had 18 pages satisfied out of that resource. If I eventually run out of real memory, then I'm going to end up seeing page swaps kick up. But stealing doesn't necessarily mean that I'm short of, that I'm actually swapping to the swap device. It means I'm recognizing there's a shortage of memory and I'm giving it to the kernel to resolve.
So Dave,
Yeah.
based on what you were saying earlier about configuring swap in 6.5 to be as large as your physical memory,
Yeah.
that would kind of imply that you could have a situation where all of your pages are swapped out? Or as many?
Not all. The entire process will not swap. But yes, if your limits are set real low, a majority of your process could get pushed out. And that gmem usage program region viewer would show you that they're out on the swap device. So then you're getting into a swap thrash situation. Now there's a limit called Rss Current Limit and stuff. If that were too small, all of your shells and stuff could actually be, every time I run short of memory, I push down to current, Rss Current. And if that's real small, it may actually be hitting all my executables and stuff too. And then I have to go off to the file system to get those text pages.
So does it steal pages that haven't been referenced yet, which are called valid pages?
It has a priority scheme and it will look for invalid first. But then when it goes to valid, it's got to look at priority and last time it was referenced and stuff. So there is an algorithm in how it sorts through the pages. And vhand, by the way, will never steal pages from Miser work. Miser is a CPU memory scheduler. We're going to talk about it later. But it's a reservation scheduler. Miser's like calling the restaurant saying, I got 10 people, I want to be there from 7 o'clock to 9 o'clock, we want 3 tables. And then the restaurant looks up in a reservation book and says, yes, I've got space for you. Or no, here's the window that I do have time for you. And Miser basically has a reservation book that it keeps track of all these reservations in. So work running under Miser will never have pages stolen from it. It's not, vHand is not aware of Miser work. So it'll steal from the interactive user before it steals from real-time or some of the other processes, but never from Miser. So vHand is called the page stealer or paging daemon, and its job is just to keep memory free. There are a couple of thresholds. Again, with systune, there are two parameters called gpage high, gpage low that say how much memory am I going to try to keep available. If I run smaller than gpage low, vHand will wake up and start stealing pages. And it will steal until it reaches gpage high. So if gpage low was like real small, 10 pages, I may go all the way to the end of my memory before I recognize I got a problem. And then it's going to start stealing pages until it reaches gpage high. And if gpage high is real big, I may have a long paging interval where the thing comes in, kicks in, and steals pages for a long time. You generally try to keep gpage high and gpage low close together. So I kick in early, but I don't page for a long time. So that'd basically be what's called thrashing situation, where it may be in a situation where it's being called very frequently with little work to do. Okay. So these are basically high-low watermarks that systune can configure. Now there are a couple other things that will kick in paging as well. There is a threshold on a per node basis. If a particular node starts filling up, we may end up stealing pages in that situation too. So here's what you were asking about. The page stealer has to decide which pages to steal. The best candidates are those with next reference is farthest into the future, the oldest. It's very hard to predict, so the common method is to use the not recently used concept. So first of all, with each page has a modified and reference bit in the page table. When a page is referenced, its reference bit is set. Likewise, when a page is modified, its modified bit is set. So when we run short of memory, vHand is going to start looking for what are called memory hogs. And memory hogs are what we're going to hit on first. A memory hog is any process that has exceeded the RSS limit plus something called RSS slop. There's RSS limit and RSS hog slop. So if the process is over the two of those, it will be a candidate to have pages stolen from. Okay. So it first selects those that have their reference bit clear, meaning that they have not been referenced in a long time, and then pages that are not included within a working set are ideal candidates. If that does not yield enough pages, and by the way, it steals pages round robin among all the processes that are hogs. So this is where the schedulers don't come into play. Every process is going to get hit. In particular, every process that's over, there's an RSS current plus RSS hog slop. Yeah, I know, hog slop. That's how much we can slop over the current before it gets marked as a hog. So like in the cray world, when we make RSS hog slop real big, that's acting more like a cray machine where we can be a bigger hog before we get pages stolen from us. So basically our entire program can sit in memory, at least stuff that I'm physically actively referencing.
So that term was invented in the Midwest, I suppose?
I don't know. And again, if it doesn't yield enough pages from the ones that have not been referenced currently, then it's going to select those that have been referenced but not modified, and then the last ones it's going to page steal from are the ones that were modified. The thinking being that if it's being modified, there's a good chance it's being constantly being used. So we're going to avoid the modified pages as much as possible. Eventually, most of their pages will have their reference bit set, so this page stealer makes a sweep through memory, clearing the reference bit of every page in memory. So it's a kind of a housekeeping cleanup. And page stealing isn't bad. It's when I get a page stolen that I'm using. What's bad is when I reference a page that's sitting out on swap because of a memory shortage. I have no problem with page stealing. It's a matter of what do I have to do to get the page back should I need it. It's the re-references that matter. So continuing on, when I get that page, if the page belongs to the process text area, that's a read-only, the pages cannot be modified. The page is simply put back on the free list. So if it's an executable portion, I just free it up. I don't have to push anything out to swap, and the executable is sitting out on the file system. So there's no sense in doing anything with it other than just releasing it. If the page belongs to a data or stack, those pages can be modified. The page has to be first written to the swap device before it is placed on the list of free pages. So if I run short of memory, I've got to get it out of the system and mark it as swapped and make sure the data that was in that page is backed up. And they often refer to swap as backing store. Same name, same concept. Under heavy loads, it's possible for a process to have less than its working set of pages available. For example, if my RSS limit was real small, if RSS current was real small, the shell itself could be impacted at some point, where every process on the system starts having to go to the file system to get executable portions of the program. So that can lead to excessive kernel paging when I pushed it down too far and have oversubscribed the limits of the system. And this thrashes on every active process on the system. There's no granularity to say based upon your priority or anything like that, only steal pages from one particular class of programs. And we'll talk a little bit about this, but bottom line, I tell people SAR-W, what you don't want to have happen on a production system is the block swapped in, B swap in. If that's happening, that's indicating you're referencing pages out on swap that you have to bring into memory, and that means you're waiting for the physical I/O of that page. Okay, I don't care about outs, because I could allocate an array and get it all pushed out and never reference it. That's not going to hurt me so much. The swap I/O path might. If I'm swapping to root, my root might get busy for the swap outs. But in terms of the program itself, what I care about is when I reference a page, did block swap in kick up? That's the one that you would prefer to avoid happening, which is the indication if B swap outs are going up, that's not so bad. But if B swap ins are happening, that's an indication you've oversubscribed your memory. Let's see. Now this page is wrong. Batch critical work never has pages stolen from it. Okay. When you reserve things with Miser, it's a guaranteed reservation. Miser will look up in a reservation book and say, yes, you can have memory, and like it's coming up to 12 o'clock, so I could submit something to Miser, and it'll say, I've got a reservation slot available from 12 o'clock to 12:30, and it will reserve that memory for you, and you are guaranteed that memory in that time slot. When you submit the work, it'll kick back the time that you got scheduled. So it'll tell you, here's when you got scheduled, here's when you are guaranteed your CPUs in your memory. So with batch critical work, with Miser work, you're guaranteed the CPUs, you're guaranteed memory. The intent of that is to have predictable timings on the jobs. Whereas outside of Miser, it depends upon system load. I could have pages stolen from me or cache thrash effects, all kinds of different things. I'm not guaranteed the resource, I could get pushed out. So page stealing is based upon priority. It does lowest priority first. It will look for what's called wait lists. And wait list is when you nice 19. So when I give up my nice value, I'm going to get pushed into the wait list category. Now a lot of sites do this for what they call the low pri queue. So they put things into the low priority queue, possibly not charge the user for anything, and then they run in a low CPU priority band. They're the ones that are going to have pages stolen from them first. Then I'm going to run into what's called Opportunistic Miser, or batch opportunistic. If I asked for Miser and it said you get it at 12 o'clock, but it's 5:02, I can run opportunistically in the next 4 or 5 minutes until my reservation time comes up. To me, this Opportunistic Miser, I always compare to hanging out at the bar before you get your table. Oh, and by the way, by the time you get your table, you may no longer be hungry or have spent all your money. When you run in opportunistic batch, you're going to get cache thrashing more than any other time. You're going to have just enough time to load your secondary cache, and then the scheduler says, oh, somebody did an LS. So you get kicked out, and then when you come back in, all the stuff you had in cache isn't there anymore. So the The more towards the bottom you are on this list, the more cache thrashing effects you have. Okay. So Opportunistic Miser is saying, if the system goes idle, rather than go idle, let's run this miser work. But I'm not going to give you a long enough time slice to make that productive. I may interrupt you before you even get your data loaded into secondary cache. Oh, and by the way, I'm going to charge you for doing it anyways. This is a problem that we're going to have to deal with. When I run a program over and over again, I want it to cost the same. If I charge $1,000 a CPU hour, I don't want it to vary $5,000 one run, $500 the next run. I want repeatable charging. This is a problem in the Irix world and in cache-based machines, because the system load can cause my service time to go up, and I get charged for that, even though it wasn't my fault. Somebody kicked me out of the CPU, dirtied my cache on me, and when I came back in, I had to reload all my cache again. It's kind of like the housekeeper that gets kicked out and the bathroom's being used all the time. Timeshare is the interactive band. That's where all of us are presently running. So when you're logged in, you can look at a timeshare band. By the way, PS is going to show you which class you're in. There's a -C option. And it shows here that my class is timeshare, or TS. And in a Cray market, we've always been timeshare. None of these other concepts really exist within the Unicos operating system. So timeshare is where most things are running, and it is driven by what's called earnings, and this is kind of like fair share. How many people have heard of fair share, out of curiosity? Fair share tracks your CPU use, and if I overuse my CPU resources, I will be penalized. So if I have Army, Navy, and Marines trying to share the same machine, fair share is going to try to achieve that distribution. Well, this is kind of like that. As I'm consuming CPUs, I'm going to have an account that's keeping track of how much earnings I've spent. And based upon my nice values, my earnings may go more quickly. If I have a high nice value, I may spend all my money real quickly. If I have a low nice value, I may spend it a lot slower and therefore be able to get back to the CPU more often. So let me try to summarize this, and we'll take our lunch break here. When my CPUs go idle, I've got job classes, and it looks for the work in these different classes. When a CPU goes idle, it looks for real-time first. That's pure priority driven. We've never had that concept in Unicos. The second level is batch critical, or what's called miser. We've never had that in Unicos. Then we look for timeshare. If we find any work in the prior two classes, we don't go on until, if we've got CPUs idle. If we find something and there's no idle CPUs, then we don't go any further. And then within each class, we schedule differently based upon the class. Real-time is pure priority driven. Batch critical, or miser, is basically reservation driven. First in, best fit. That's the best way to describe it. First one to the restaurant, based upon the size. If I go to the restaurant with one person, I got a better chance of a table than 20 people. Then within the timeshare, we figure out, if there are several in the timeshare, we figure it out based upon earnings, which are kind of driven by the nice value, but not directly. In the Cray world, we used priorities in the timeshare band, and fair share manipulated those priorities. Here we don't have that. And in the Irix world, priorities do not shift around. They stay the same all the time. You don't have shifting priorities like fair share does in Unicos. And then lastly, also I was trying to say is the CPU priorities are scheduled one way, and memory shortage, when I steal pages, we're going the other way. But again, batch critical and miser will never have pages stolen from it. And this bullet here under batch critical, you can kind of crop this out. Batch requests are submitted to miser, and that you specify a CPU time, and then you get placed into the opportunistic class. If the job doesn't complete by your reservation time, the best way, not in specified interval, but if you don't complete by the time your reservation comes up, then you go to batch critical, and you get higher priority. Okay. So it's kind of a poor wording here. We're going to see this when we actually do this, but with miser I say, I need this much CPU, I need this much memory, and I need this number of CPUs. Okay. And then the kernel is going to look in this reservation book and say, oh, I found a reservation from 12 to 1. The resources are available there. That's your scheduled time. Until that time comes up, you're batch opportunistic. You're going to run in batch opportunistic. But if the job cannot complete by the reservation time that Miser is reserved for you, you then go critical and are able to use that reservation time. Now, if I finish early in my reservation time, the rest of the Miser cannot schedule the rest of that reservation block. So if I, for example, asked for an hour and finished 45 minutes into it, I may have 15 minutes where Miser says, you reserved and scheduled it, I can't give it to anybody else in Miser. But interactive processes can steal that stuff. So when Miser's free, timeshare can always take advantage of those CPUs. It's dynamically switching over. But if Miser critical work comes up, then we're going to schedule that stuff immediately. And you'll go batch critical, BC. And waitlist is basically when you're running at a nice of 39. And with that, I think is a good time. But just make sure, scratch out batch critical there. We never steal pages from it. And then the concept here is it's not in specified time, it's in the time reserved by Miser. What Miser has specified is your reservation time. Not what you've specified, but what Miser has told you is going to be your reservation time. And with that, let's take our lunch break. Come back about 1 o'clock. So I won't put it up there. We're in the middle of talking about memory management and demand paging, and talking about two different issues. Virtual memory is one thing, and then demand paging is a separate thing. Virtual memory is how we address things using TLB buffers and page tables to translate from virtual to physical addresses. Whereas demand paging is what do I do to get to the page? How do I get to the page? If it doesn't exist, I got to create it. If it does exist, I got to find it in memory, in cache, or out on disk. And we're going to get into some of the SAR metrics that describe these different behaviors. There are a lot of traditional Cray customers that I think could be taking better advantage of virtual memory than they presently are. Particularly like University of Dresden and a lot of these sites, they're running chemistry codes or sparse matrix solvers. And we're going to get into some of that a little bit later. There are a lot of sites out there that are still trying to oversubscribe memory and constantly swap all the time. But the penalty there is you've got no control over who's going to do the paging and stuff. And it's going to be non-discriminate. So again, the key thing is to not oversubscribe basically any resource in the system. CPU memory, cache, we're going to look at all the different resources. So when we do run short of memory, vHand kicks in and tries to recover memory by stealing pages from processes. And basically, as long as there's no memory shortage, a process can grow as big as it needs to in memory until it hits a limit. And there's an RSS virtual limit, VMEM limit out there. So you can grow until you hit that limit, and then you basically get killed for exceeding limits. And if you're not short of memory, the entire process can be sitting in memory. A lot of traditional Cray people try to get the virtual and the RSS size to match, but that is not a requirement here. As long as you're not paging, it's not a problem. Okay? So we're going to come back to that, but paging was visible by SAR-P and SAR-W. And the bottom line was with SAR-W, our blocks paging in high, because that says I'm referencing data that has been pushed out to swap that I need to bring back in, and now I got to wait for the disk drive and the I/O path to get that page into me. So just before break, we were trying to talk about the fact that when I do run short of pages or short of memory, I have to start stealing pages. And it looked like 424. And just saying that it uses the CPU priority scheme to determine who to steal pages from. Again, Miser never has pages stolen from it. And none of these classes will have pages stolen from that unless we run short of memory. Okay, so a program can grow as big as it needs to grow until we run short of memory. Then we're going to start stealing pages from it and pushing it back down into a more reasonable size in memory. Now, the first place when I steal a page is I put it in what's called page cache. Page cache is basically, again, vHand is passing the page to the kernel, and the kernel stuffs it into its page cache list. And then if I need, before the page actually gets pushed to swap, if I need to get the page, it's right there. Okay, and I can ask the kernel for the page, it can find it in page cache. So they got this thing called page cache, basically stolen pages being swapped out or staged in page cache. vHand shoves it into the page cache, and there's a routine or a daemon called shake D that shakes the kernel down. And it's shake D's responsibility if the kernel gets too big to push it back down again. A little bit earlier today when I had a second Netscape I fired up, we saw the cache get released and got squished down a little bit. So that file system buffer cache can be released if I'm running short of memory. Now if I'm on an NFS server, I'd like to have that page file system buffer cache real big in most of my memory. I have no problem with the 64 gigabyte kernel if its job is to hold I/O data, and the I/O data is sitting there in file system buffer cache. Okay. Recent case study I was involved in was a news server, you know, RN, TIN, getting news articles, and about 25% of the memory was left available, and the majority of the nature of the I/O on a news server is inodes. Every news article or every news group has a inode associated with it. So var news has tons of metadata, inodes and directory blocks that you have to go through. Now on this news server, gross view showed that that metadata was very, very small in memory, and then a majority of memory was being used for non-productive work. So by configuring, in this case it was a parameter called NC size that said how big of my cache can my inode data get to. And by upping that, we were able to hold more inode data, and then the system wasn't as IO bound, thrashing on the inodes. So this page cache can be to your advantage. Yeah?
Just a short question, you don't have to answer in much detail. We're talking about how the operating system manages memory. Is there some strategy for the user to manage memory on their own?
No. I mean, malloc is all there is. There's no heap management like we've had in Fortran, in Unicos or anything.
You're pretty much...
You ask for memory when you need it, and Irix's view is that you're responsible for your memory allocations and deallocations, and also responsible for what to do when there's not enough memory. In other words, if I ask for memory and it's not there, I don't want to die. I'm going to try to go off and do something else and then come back and try for that memory again.
But if you get into some segment of your program where you know you have a lot more memory than you need to release the memory, or do you rely on the operating system?
Well, through your mallocs and deallocations, you can release memory through deallocations. Most programs don't do that. Okay. You know, a lot of this just goes back to the programmer.
Right.
Is there an incentive or not?
No.
There's no incentive.
Now, the bottom line incentive truly is that we haven't seen this here, but when you really run out of memory and swap, things start getting killed. And if you've ever been on your workstation and Netscape gets killed because you had 3 Netscapes up and you ran out of virtual memory, for example. And that'll happen on a Cray too. When your physical and your swap are all full, we're in a deadlock situation. We can't even kill the processes because their process information, the user.h, is out on the swap device. So we can't even send it a kill signal in that case. Whereas on Irix you can. But no, there's not a whole lot of memory management. They solve the problem by throwing lots more memory at the system. And memory is a lot cheaper and a lot larger memory systems than we had a long time ago. Of course, they're slower memories too. And they're not interleaved as heavy as we've done in Crays down to a word level. So at the most you got 64 nodes, which again is like a bank, so I can interleave 64 page requests at the same time on that system. Anything else? So anyways, basically the page is going to get marked. There will be a marker in the page table that says that it's invalid. A stolen page placed back on the kernel's free list is marked as invalid. So I push the page into page cache. The kernel then pushes it out to the swap device, and I can mark the page as invalid, meaning that it's reusable, and put it on the free list. And then if somebody else needs memory, they go down the free list and find a page. If the page belongs to a process data or stack areas, then it's going to be written to the swap device before releasing. If it's the text portion, we just release it, because the text portion exists on the file system. And again, we're just passing the buck to the kernel and stuffing memory shortage problems in the kernel and saying, kernel, you take care of the problem. And it's this thing called shake D then that's going to say we still got a memory shortage, and we'll push those things actually out to the swap device. So page cache is really just a staging area. And it's useful if I'm re-accessing the data. It's not useful if I'm oversubscribing and not reusing the data, because now I'm putting loads on the page, on the file system buffer cache threads and asking, shoving data into it. And if I'm not reusing it, there's no sense in caching it. But that's the way the operating system works. Irix is designed for interactive workstation environments. When we implemented Unix on Craze, Unicos really optimized for scientific, whereas this is optimized more for real-time and interactive environments. Let's see. So this thing, page cache, is basically saying that I'm going to take it out of the memory management pool, put it into the cache, file system buffer cache, and then let the kernel worry about it from there. And yeah, it says here shake D is going to basically write the stolen pages to the swap device. Then when the pages are sitting on swap device, there's a process called reclaim. And SAR-P is a metric that says I had to go to the swap device to reclaim a page. And those are bad. You don't want to have reclaims when they're coming from the swap device. By the way, anybody that works with accounting data like JA or something like that, waiting on a page from disk will show up in your direct I/O wait time, and waiting on a page from cache shows up in your cache I/O wait time. And then the Tlb misses themselves show up in your user time. So it says here, page cache allows the page stealer greater performance because it doesn't have to wait for completion of the physical I/O. It can go back to recovering memory. Meanwhile, the kernel now has to have the problem of pushing that down. Some of the older systems, like 6.4, this is not working correctly. Your kernel may grow and not get released or pushed back down very quickly. It's a real problem. This is why I advise you go to 6.5.2M, because they fixed some of the stuff, which they did not fix in 6.5.1M, the last I looked. But if that kernel gets real big, and then you throw a big memory problem at it, it should push the kernel back down. Now what do you do though if the kernel's on a 64 gigabyte system, it sucked up 60 gigabyte of I/O, delayed write dirty data that's now got to flush to disk at 5 megabytes per second. Then it's going to take a while for the kernel to get pushed down when it's got to push 5 megabytes per second out to a disk drive. But you got 64 gig of it sitting there.
Dave, what's the difference between 1M and 2M?
1N and 2N, I'm not following the question.
651M.
Oh, 6.5.1M came out, 6.5.2M hasn't come out yet, not much difference. They're both maintenance releases. We've gone into a split tree where we've got Fs and Ms, and an M are just the patch sets all grouped together. For me, a lot of it's been kernel changes going on. When I go to 6.5.2M, the patches that are in the kernel are the reasons that I've gone to 6.5.2. And the other reason is that Mountain View and Software Division doesn't want to work on old products, 6.2 or 6.4. They don't even want to work on 6.5. They've got to work on the problems they're seeing on the latest and greatest cut that they've got. So for us, it's to our advantage to go with the latest cut that has been MR'd. MR standing for manufacturing release. Okay. But I can't get into the details. They're patch set differences and behavioral changes. I've been pounding on Irix for 2 years, and every time I run a class, I go with the latest Irix cut, and they've been different in every class in terms of behaviors and predictability of whether this knob works or not. And nobody's testing this stuff. They test basic functionality, but they don't test behaviors when you overload systems or things like that. They don't test to see, does the kernel actually get pushed down in a timely fashion if I grow the kernel and then have a user try to take all that memory. There's nobody testing that sort of thing, except for the developers. And that's like, fox guarding the hen house. Let's see. But if a process reaccesses the stolen page and is still in page cache, then we don't have to wait for the swap device to get it. So by shoving the page into cache, it just gives us a little bit more breathing room to be able to reuse the page before we actually go through the physical I/O out to the swap device itself. And again, this is just trying to show that vHand is going to steal pages from processes, shove it into page cache, and then it's shake D that's periodically going to wake up and try to push the kernel back down. Again, assuming there's only a shortage of memory. If there's no memory shortage, vHand and shake D really don't get involved. Okay. And historically, shake D was using the time of the last shake to schedule the next shake. So if I had a 64 gigabyte system, kernel grow, it may take me several minutes to push that back down. It's going to use the time that it took that shake to start the next shake. So if it took 2 minutes to push the kernel back down, it'd be 2 minutes before I wake up and recognize that there's a big kernel and try to push it down again. And this has been a problem, and in 6.5.2 that I'm running, they've changed that behavior. So that, well, basically you're going to shake once a second. They've got a parameter now that specifies how often am I going to shake the kernel, rather than using the previous shake as the timing to do the next one. We had the same sort of problem with SSD and LD cache, and processes would be sitting there taking up all LD cache, and then we'd oversubscribe the SDS space with a sign and have stuff flushing between one side of the SSD that was configured for LD cache and the other side that was flushed with SDS. And then maybe we had checkpoint files going on in that same cache mechanism and oversubscribing that sort of resource and thrashing on it. They show here in shake D, there's a shake D interval, and it's basically set to 1 second. I don't know of anybody that's actually changing it or manipulating it. Basically, everyone's sticking to 1 second. If it gets longer, then your kernel's going to grow, and it's not going to recognize that it's too big, and it's not going to try to push it back down. But the intent of being able to slow it down is if I'm on a large system that's constantly got a large kernel because it's an I/O load rather than a CPU or memory load, if this thing gets too big, we don't want to start the next shake before the previous shake is done. Probably 8 years ago, I'd use the accounting data and look at how long the LD cache command took. And it'd be syncing like every 2 minutes. And if the accounting data said it took 5 minutes to do the LD cache sync, then we didn't want to do it more often than the previous one was finished. So it's the same kind of thing. You got to figure out how long it takes to actually push it down and make sure it doesn't start the next one until the work of the previous run is finished. And again, systune is what controls all this. All of our system configuration parameters are in that var sysgen mtune directory. And even on your workstation, you can get in there and take a look at these configuration files. But you'd need to be root to actually change the value. So even though it's describing 1 second here, that behavior has changed in several releases. So text pages are read-only, stolen pages are not swapped, but simply released and then reread from the file system when needed. The data and the stack are what are called anonymous pages. They're not associated with an executable file. And then these data and stack regions are writable and the pages are generated when needed. In other words, on demand. So demand paging says, create the page the first time I reference it, and then depending upon the demand on that page, either keep it in memory, cache, or out on swap. And if I never demand the page, it doesn't matter if it's sitting out on swap. So basically, I guess, anonymous pages, memory pages associated with the process that are read-write. If it needs to steal an anonymous page, it's got to allocate space out on the secondary storage, which is the swap device, also called backing store. Those are common names for swap. Now, the swap device is configurable on the fly. What we've got here is basically the kernel showing a swap table. There's a command called swap that prints out the contents of this. Now, traditionally, swap is en route because I'm on a workstation and I've only got one disk drive. That paradigm's still there. If I get a large Origin 2000 with 128 disk drives, my swap is still en route. Number one rule we learned in Cray was to get any I/O traffic off a root that wasn't associated with root. And we started building swaps off on separate devices. So the worst thing in the world is to have swapping going onto your root device. Now with the swap command and additional disk drives, we can add additional swap partitions and then get our I/O traffic off to a different device. I don't want my root device where LS is coming from, for example, to be tied up by a large, 1 gig process that's actually moving data out to that particular root. My worst case scenarios in the tuning class is when I try to do all my I/O to root, where I do NQS traffic there and various other things. In fact, last week I had a problem. There's a new tool called Irix View. Anybody used WinView? WinView we've been using in Unicos on the VxWorks operating system. Irix View is a GUI to look at some event logs that you can track with commands like par, which is a process activity report, gives you system call information and process switching, and also something called RT Mundy. Anyways, I looked at about 5 seconds worth of system activity last week with Irix View and was creating 20 gigabyte files, all going in var temp and filling up my root device. And all that I/O pounding on root was really slowing the system down. So Irix View is a great analysis tool, except it's a GUI and it's looking at hundreds of thousands of events, and the temporary files that it manages are huge. It can really slow the performance of your system down as you're using the tool. In terms of performance impact, Irix View is probably the biggest one out there because of the large files that it's doing, and they're all going into var temp, which traditionally is on your root device. So any anonymous page associated with user process has to be pushed to the swap device. The kernel maintains this mapping between the anonymous page and the swap device. There's a bit in the page table that says it resides out on swap. Irix must have at least one disk partition or file allocated for swap space. And then you can add or delete swap areas as needed. And you can do that on the fly. I can actually delete all the swap space on the system and then add new swap space, as long as what's currently there isn't active. If I actually have active stuff out on swap and I try to delete it, it'll tell me that it's busy. But a lot of this stuff can be done just on the fly as needed. All this is done with the swap command. Okay, so let's see. And what it's going to try to do is push all the pages across all swap areas of the same priority. So you can tier your priorities. Now root is still the highest priority. And then you may be swapping to additional swap partitions that you've added, or you could swap to a file system swap partition, or you can even have pages being pushed to an NFS mounted swap device. That'd be worst case scenario because I don't want paging activity going across my network if possible. So the swap command is how I administrate all this stuff. I can add, delete, set priorities, things of that sort for this swap partition. And again, the rule of thumb in 6.4 was we were setting our swap space sizes based upon what I needed for a dump. So it's typically 512 megabytes for 32 CPUs or less and 1 gig for more than 32 CPUs. But in 6.5, I advise people to go 1-to-1. So if I have a 64 gigabyte system, that means I've got 8 or 9 optional drives out there just for swap. So they got the swap man page here. A will add, D deletes. L will list what's presently configured. I'll talk a little bit about S later. Swap-M just mounts all the swap devices that are in its FS tab. And then lastly, a -U. And here they've done a swap-L, and we're looking at 4 partitions. If you're familiar with the naming convention here, dev disk, DK for disk, S6 says that this one is on SCSI controller 6 and it's disk 2. Also have SCSI controller 6 disk 1 as a swap partition and SCSI 1 disk 1 as a swap partition. After that then is the priority. The lower the number, the higher priority. So I'm going to swap to swap first, then I'm going to swap to S6D1, then S1D1, and lastly to S6D2. Now if they were all at the same priority, then I would round robin my pages among all 3 swap partitions. But because they're all at a different priority, I'm going to fill up one priority, then the next, then the next. Now some people seem to think that striping swap is to your advantage. Striping is only as good as the request sizes you're making to it. If my pages are 16 kbytes in size, the default stripe unit in our file systems is 64 kbyte. I need to get transfers over 64 kbyte before I actually start using more than one drive of the stripe group. So the only time I advise striping my swap device is when you go to large page sizes, because you can specify a larger page size up to 16 megabyte. Then I'd start considering striping my swap to a 16 megabyte stripe width, such that when I do an I/O request, that 16 meg gets broken up into equal pieces and sent off to all the individual partitions of that stripe group. And by the way, not much listed here, but there's a new command in 6.5 called disk align that gives you guidelines for setting up stripe widths. It's primarily designed and written in the entertainment market for video streaming. So the examples on the man page figure out how big is a video picture, you know, pixels times frames, number of lines, and all that sort of stuff, and then comes up with the amount of data in a single video image, and then sets up striping widths based upon that. And we'll get into striping a little bit later. But what I was trying to say here is that in this example, they've got 4 partitions all at different priorities. So I'm going to see the bandwidth of one drive at a time. I'm going to fill up the first partition at 0, then I'm going to fill up this one, then I'm going to fill up that one, lastly I'll fill up the third one. If I had put these all at 1, then I would have round robin the pages among the 3 disks and gotten better performance, because I can distribute 16 KB pages around those 3 disks. If I stripe them, it'd still be acting as a single drive. And I'd rather not stripe unless I know I'm using large page sizes. After the priority, we've got basically the blocks, how much free, it's doing swap low, beginning of the partition, number of blocks to the partition, how much is free, what's our maximum, and then there's something called virtual swap. Virtual swap is like dev null. Virtual swap does not really exist. There's actually a /dot, there's a file in root that's touched when you boot the system, /dot virtual swap, but there's nothing to it. Virtual swap is pretend. It simply allows me to ask for memory, but if I don't use it, it makes things go quicker. Virtual swap would help me. I do advise traditional Cray customers to look at virtual swap because I can get more things in memory. I can have higher memory utilization because my programs don't always use all of the memory that they've asked for. So virtual swap helps me in that area. It extends the life of the system. However, when virtual swap is turned on, the kill decision is changed. With virtual swap off, whoever's asking for memory will be denied the memory. Whereas with virtual swap on, the largest thing on the system is going to get killed. And in the Cray market, the largest thing on the system is usually my bread and butter application. That's why it's so big. Same thing on database markets. The database engine may be the largest thing there. So traditionally, SGI says don't turn on virtual swap because your bread and butter application may get killed when I run short of memory. But again, in any situation, no matter what you do, you're eventually going to oversubscribe memory, and having virtual swap on may extend the life of your system before you hit that deadlock situation. Now these swap resources have an allocation. There's a swap-s command that says, again, as I mentioned earlier, there are 2 levels here. There is a reservation and then there is an allocation. So when I do the malloc and ask for memory, it's going to be reserved for me and carved out of the entire virtual memory pool, including virtual swap. And then once I actually touch the data and allocate it, it goes to the allocation state. So I've got an example here where 2.3 gig are reserved, none are allocated, and I've got a 30 gigabyte system that's available. Okay. And that 30 gigabyte might have included virtual swap. In this case, it doesn't look like it. And also then the swaps are based upon priority, 0 being the highest priority, 7 the lowest. And within a priority, allocations are done round robin among the disk drives within the same priority. And by default, block devices are priority of 0. You can swap to a file system through buffer cache, which is a priority of 2. And you can also have NFS file systems with a priority of 4. And there's a command called make file in Irix that allows you to make a file. So you may actually do a make file. For example, 2 a.m. on Christmas Eve, you may detect there's a memory shortage by a cron event. You could do a make file and then start adding to that swap partition this temporary space. Of course, you would not want to run that way production all the time. And Miser, by the way, is part of that reservation. You could have the scenario where gross view doesn't show you the reservation, but in fact, Miser is. It will show up with swap-s. So I could see lots of memory available, but I try to fire off a 1 gig process, and Miser's already reserved 1 gig process, or 1 gig space, so you might not actually get it because Miser's pre-reserved it. And if you're not using Miser, don't turn it on. And we're going to come back to Miser in the next section. So this logical swap, memory requests during a fork, you have to allocate memory for the child. And then the malloc itself is how we ask for memory, and library routines may automatically do mallocs within them. And then this is allocated from your logical space. I kind of hate the term here swap space, but your virtual memory addressing space is physical memory plus all of your swap space added together. So they're calling it logical swap is the sum of physical plus all the swap devices. I prefer to call that my virtual memory addressing space. But again, there's virtual swap added in there. So this is what I can really use. And it allocates it, fork obviously did it as I mentioned, but then there's also break and S-break and malloc, which is the C library routine that does a break or S-break. Couple other things, shared memory. If I allocate shared memory, it's going to also allocate out on swap. And for crazy people, again, this stuff is new. We traditionally have not had shared memory stuff in our operating systems, and the applications running there don't use it. But I had a case where at University of Dresden, we had applications that were using shared memory. It was Gaussian. Never used it on Unicos, but it did on Irix because it was there. Problem was that NQS was killing the jobs before they could release their shared memory space. So their swap allocations were just going up, 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 up. And it's in a shared memory environment, it's up to the application to release that shared memory space when it's done. And because these things were being killed by NQS limits before they could do that, I basically had what looked like a memory leak. And there was a command called IPCS. If you're new to interprocess communication, IPCS lists me my interprocess communication resources. And there was a -AM that we did, A for all metrics, and then M for the shared memory. And it showed a lot of shared memory that was called non-attached, N-attached. One field saying that there are no processes attached to the shared memory space. So then we were basically, through a cron event, running IPRM, I think it is, or IPCRM, to remove those unattached shared memory segments. So shared memory allocates out as swap, and you won't see this. There's no command in Irix to tell you what's actually out on swap or consuming that space. In Unicos, we've got the CSAM, XSAM type of interface to show that. One other thing that is not mentioned here that is allocated on swap as well, and that's pinned pages. You can lock a page down in memory such that it can't be moved. Pinning a page. P-lock, process lock, P-lock type of interface. Those will also have reservations out on swap. And again, a lot of this area changed from 6.4 to 6.5, so you got to be real careful about it. When a process requests more space, if the amount of private space exceeds the system's available space, then the system call will fail with an EA again type of error, and you'll get this out of logical swap space message. And again, if Miser had been started up, you may actually get that early, because Miser may take a gig of your memory pool, and now you're fighting for whatever's left over, and you don't know about that Miser memory release or reservation, even though nobody's using it. Miser has still reserved it. And again, it's up to the responsible programmer to prevent memory deadlocks from occurring and basically check your malloc returns and memory growth returns to make sure you got it, and hopefully do something responsible rather than just say no memory and die type of situation. And I have had a lot of problems both in Unicos and in SGI with an NQE where I have memory limits that are enforced on a per job basis, and compilers that hit a memory limit don't check their error status, and then you get a loader that says the subroutine isn't in the source. You go back to the source and it's there, it's just that the compiler truncated the table. And that has happened both on Unicos and Irix. So avoiding swap space exceeded errors. The out of swap space errors may be received when large programs issue a fork which duplicates their address space. There's nothing in Irix right now like vfork, which is designed to fork a child without the memory footprint. For example, in the seismic community, it's not uncommon for the petroleum sites to have an application that does tape mounts from within the Fortran. And the tape mounts are going to be using a library called named system, which forks off a child and then invokes the tape mount commands or the tape release, tar, those sorts of things. Okay, also programs have to dynamically allocate large memory regions through malloc and then release them. Debug your large programs, make sure they're not memory leaking. There is a program there called Purify that's designed to check programs for memory leaks, but it only works on 32-bit binaries. It's not supporting 64-bit binaries on Irix yet. I logged into this University of Dresden one and ended up having 2 memory leaks. One was shared memory segments that weren't being released from job kills, but also another program called C-Collect, which is part of the NQE data collector. And it had a memory leak in it such that it was 1/3 of the memory on the system. And its whole job is just to collect data for load balancing across multiple NQE domains. So what can you do? Add more real swap space. Again, I don't necessarily agree that we have to continue oversubscribing these systems like we did 10 years ago. A 20-to-1 memory subscription ratio was not bad when we were a 1 megabyte system or 1 megaword system. Nowadays, when we're talking 64 gigabyte, these are huge systems, and trying to maintain a swap partition that's 10-to-1 or 20-to-1 your physical memory doesn't make sense. And memory sizes are just going to get bigger and bigger. So you can add more real swap space, but there's a dead end at some point there. Eventually your entire disk farm becomes swap, and then you can't do real I/O. You can allocate additional disk partitions off of multiple drives. In my data center in Egan, we have multiple routes on our system. So there's routes A through F. My route happens to be route E. Production route might be route C. Not only one route is active all the time, but all the routes have a swap partition on them. So I can take advantage of all those other swap partitions. Rather than waste the bandwidth that those drives can offer me, I can mount those swap partitions and never even have to use those root file systems that are on those devices. You can allocate additional swap through a local file or NFS. Again, those are the worst. They're going to push your file system buffer cache worse, contend on the system much more, and also then start pushing across the network. When I was at Lanel, that was their biggest problem. Everything is across networks, NFS, everything. And in the SGI world, they seem to think that I should be doing production I/O across an NFS-mounted file system. And that's not the best way to go, because now you're doing I/O across your network. Also a required approach that programs that access most of memory, they allocate, manage that properly, and release memory that they're not using. As we discussed earlier, many programs, especially in the Fortran world, take memory but never give it up. Very rarely do you actually see it releasing memory. Now you can add virtual swap. Again, virtual swap is pretend, it's never really there, but it increases the amount of logical space you have without adding any physical disk space. So it's pretend swap. It gives you extra breathing room before you hit that deadlock. So if I've got memory reservations that are going on that I never use, they can reside on virtual swap. As long as I never touch the page, I can keep going. So by turning on virtual swap, you're actually extending the life of the system before you hit memory full in a deadlock situation where you have to start killing. In my tuning class, I've got this one code that goes to about 500 megabyte in size. And with virtual swap off, I can run 2 or 3 of them. With virtual swap on, I can run 10 of them. So virtual swap can increase my memory utilization. It gives me more breathing room for the operating system to work in. The disadvantage is the kill decision has changed. When I turn on virtual swap, the largest thing on the system will get killed. With virtual swap off, memory will be denied, and the application has to properly handle that memory denial, which is usually a death. You know, I kill myself rather than let the kernel kill me. Not too many applications will sit there and wait for memory to free up. Hopefully database engines and stuff do, but I haven't looked at them. And I'm seeing these messages, by the way, a lot more in 6.5 because of the reservation schemes that have changed. So virtual swap, they're just trying to show here. I've got swap, and then I've got a pretend virtual swap. It's actually a file in root called /.virtual swap, and it's touched when you boot the system. Doesn't require any additional memory space. Disadvantage is that it adds risk of encountering memory deadlocks. I don't like that phrasing. It actually reduces the chance of memory deadlocks unless I really do use all the memory space. So it gives me more breathing room if I don't use the space. But eventually a deadlock has to be resolved by killing something. So since virtual swap has no associated space, a memory deadlock could occur, and in that case the kernel has to kill the process to free up enough logical space to break the deadlock and have enough breathing room to keep running. And processes are killed based upon priority. The lower the priority it is, the size, start time, and whether it's a parent or not. We will kill children before we kill parents. Anyway, time to close the front door, right?
Yeah.
Virtual swap should not be used in cases where the program will attempt to use the memory. Otherwise, processes are killed. So you'll see all kinds of warnings about keeping virtual swap off. And in my class, virtual swap actually helps me. This is going to be a political area. In fact, in 6.5, they've got 2 levels of virtual swap. One that's always there, and then one that can be turned on. And swap-ln is the main thing that I would be concerned about here. Let me go off to my workstation here. Swap-ln lists my swap space. So here I've got 1, 2, 3, 4, 5 physical partitions and also a virtual swap partition. I see the priorities at 3 different levels. So in this case, I'm going to swap to my root first. Now, I'd rather delete dev swap and then drop it at a different priority. In fact, I may as well do this here right now. So I'm going to do a swap-d/dev/swap. Oops, spell it right. And if it were actually busy, it would deny this delete if there was actually stuff allocated on it. And in fact, it looks like it did, but it looks like it moved it off to maybe one of the other partitions. Let me see what happened now. Swap-ln wasn't busy, but now I've got allocations spread out on this particular drive right here. So there was about 7 meg or something here that now got redistributed. A couple of meg here, 1 meg here, 1 meg here. It distributed that among the 3 drives. So when I deleted dev swap with the -d, well, let me get the right one. It moved the stuff off of dev swap and put it onto my next layer of swap partitions. Now I can do a swap-a for add, -p for priority, and I'll put it at a priority of 3. Let's see if this works. And now if I do my swap-ln, I can see it's now at a priority level of 3. No allocations occurring on it. I'm not going to allocate on that drive until I fill up this 4-disk swap partition. And now I'm on do and Egan. Let me just check here. HINV shows that this is a 2 gigabyte system. And now if I take a look at my swap, I've got maybe 1 gig of real memory or physical swap. Add this up, I get about 1 gig. But I got 38 gig that have been configured as virtual swap. And again, that's pretend. That's just extra breathing room. That's not really there. So if I did a swap-s now, it will show that I've got that 38 gig total. And right now the system has 2 gig that are allocated and 3 gig that's reserved. But do we have any swapping activity going on? I expect not. No swapping occurring there. But ps-e-l prep for Miser. I do have a Miser Daemon that's presently running on the system. Let's see. I'm just checking here. And it's asking for 1.5 gig. We're going to get into this later, but Miser, when it starts up, is actually reserving 1.5 gig, but since my physical memory was only 1 gig, it's actually going to drop that back down. Out of curiosity, I suspect I got some job kills in Miser, but not a memory denial. One of the things Miser will do is if you don't have that much swap space, it'll drop it down to what you really have out in swap and not give you a message saying it resized it. So what I was trying to do was see if swap-s, how much of that was actually due to Miser allocating out of that 3 gig. Let's go back to the workbook. So, yeah, go ahead.
You know that, when you set that up, you set that virtual swap at a priority of 2, and the physical swap at a priority of 3.
Yeah.
Are you actually going to
do reservations on virtual swap before the physical swap, yes, but if he actually allocates it, then it'll move off of virtual swap and go to the physical dev swap. So yeah, you can have them in a different priority. You could have virtual swap first as the highest priority. I've seen some systems do that as well. But again, once I go from a reservation to an allocation, it'd come off a virtual swap and go on real swap. And some of the stuff isn't documented yet, but in 6.5 now, we do have with *r, there is a virtual swap field that's configured here whether virtual swap is on or off. And as I said before, virtual swap gave me a lot of benefits. The trade-off was the kill decision. So in 6.5, it looks like they took advantage of that and had a slush fund virtual swap that did not affect the kill decision. And then when I actually turn virtual swap on, it adds to this, and you'll see this number jump up. Now, out of curiosity, I'm just going to do a check config and grep for vswap. And virtual swap is on this system right now. So I've turned off virtual swap in this example. Do a *r again. And my virtual swap is still at the same size. But now I'm going to go into itsy init.d, which is where all my initialization scripts are, and swap stop. And I'm basically deinstalling, and because I've got some allocations out on swap, it's complaining. Not enough space. Remember that stuff that moved from dev swap off to the others? Okay, but now at this point, let's see what *r shows me. And it dropped down a little bit. Not a whole lot there. Okay. So there's this virtual swap slush fund, and virtual swap, let me do one more now. Restart it this time, because I turned virtual swap off. Shut down the swap stuff with the swap script, and now I'm restarting it. It failed for one thing because of resource busy. I probably should have done a swap-ln to see what it was like beforehand, but let's see what we got now. So now I've restarted it, and my dev swap has not been added to the list, probably due to that swap busy problem. When I tried to shut down swap, it could probably not release that. Let's see if I can add it back in now. Swap-a-p3 dev swap. Okay. So now I'm back to where I was before. And let's see something here now. Oops, not the one I wanted. And my virtual swap is back up to where it was before. So the virtual swap is configured. They're just showing here, itsy config is where we've got all these files that have either on or off in them. And when you boot the system, this check config command goes into that directory to figure out whether the service is on or off. And then there's this vswap.options file that specifies how big do I want my virtual swap to be. And if I see *r in that virtual swap growing and growing and growing, I may be upping the vswap.options file until there's plenty of headroom left. And no matter how big you make it, the disadvantage to making it large is gross view. Now the GUI to look at the stuff under gross view is called SWP. And the disadvantage to having lots of swap is that pretty soon your whole memory map is going to be virtual swap. I don't know if I got a network problem here, slowness or what. Let me go off to my workstation here. So this one's showing my system on the workstation here where I've got real memory here. That's my physical memory. And then I've got my swap space here. And there is some allocations that have occurred out on swap. The last two pieces is my virtual swap, and it's not even here. Okay, but if I made that too big, the actual physical data representation of the system's virtual memory footprint would be so small and then I'd have this huge piece of my bar that's just showing me this pretend swap that isn't really there. So that swap-s command is also visible with gross view as a SWP graph within it. And I'm not sure why I didn't get a window back from the other system. Let's see. Must still be trying. So in general, people will advise you real caution about using virtual swap, and I'm trying to tell people that it may be to your advantage. The trade-off that you're making is the kill decision. Now with virtual swap space, I can dynamically configure the length. The -V option specifies how big I want it. This is what was in that vswap.options file, which was defaulting to like 80,000 blocks, something like that. And again, a block is 512 bytes. In the future, they will be upping things to 4K bytes with the next XFS file system release and stuff like that. But right now, it's all 512-byte blocks. Now, traditionally, there is something in Unix called swapper, and this is just trying to describe the concept of swapping. I'm trying to be real careful about my terminology. To me, swapping is the entire process going out to the swap device, like Crays have always done, versus a paging system where pages may be pushed to swap. And a lot of people, including myself, will abuse it and say that that's swapping as well. But there's a difference between swapping the entire process or just paging individual pieces of the process out to the swap device. So let's see. Basically, no matter what you do, you eventually get to a deadlock condition. A couple of slides ago it said, what do you do if you run out of memory? Well, there was one option not listed there, and that's put a workload control system on it like NQE or LSF that prevents the work from exceeding the capacity of your system. How many people have worked with NQS before? Few. NQS is probably going to go the wayside now. It was a traditional Cray product written by NASA Ames for the Cray 2. But we're giving it away to a company called Platform Computing, who supports a product called Load Sharing Facility in LSF. And I think LSF is going to take over where NQE was working before. NQE works on a single mainframe platform, but not in a configuration of a cluster or an array of CPUs. Whereas LFS treats a whole set of CPUs more contiguously as a single system image type of approach. It clusters better. So NQE is given away, and basically LSF is going to become the new product, if you ask me. And anyone interested in that, www.platform.com is the company. And the product is called LSF, the Load Sharing Facility. And other than NQE, it's the only other common product out there. There are a few others. There's PBS, Portable Batch System, Codeine, a few other products out there, but those are the main two, NQE and LSF. So these are just batch interfaces. These are like stoplights to get onto the freeway system. They throttle back the traffic so that you don't oversubscribe the system. We had to develop it for the Cray 2 because when we put the Cray 2 out there, 256 megahertz system, our disk drives were moving about 10 megahertz per second, and then they'd oversubscribe the system and spend minutes doing a swap of an individual process. And on Crays, when you're swapping, your CPUs go idle because that memory is not usable. So this system had a lot of idle time as it was oversubscribing memory and swapping too much. So that we initially wrote NQS to replace a product in the Cray world called JCM, the Job Class Manager, which was part of COAS back then. But this is historical. A lot of this stuff was implemented in Unicos where we added nschedv and we're able to control the scheduling algorithm based upon CPU priorities, size of the process, how long it had been in memory, things of that sort. In the Irix world, it does nothing. Swapper basically does some CPU work but does nothing in terms of managing or swapping entire processes. There are other Unix flavors that do still swap. And it's just saying here, Irix systems currently do not swap whole processes. It will be coming back. There will be in the future a policy under Miser such that the entire process in Miser can get swapped. Remember I mentioned earlier, Miser never has pages stolen from it? Well, imagine the person that's running a 64 gigabyte process under Miser and then suspends the work because it's a prime time schedule. In a lot of Cray centers, we suspend night work during the day, and then all that stuff goes out to the swap device. Well, under Irix, Miser and Irix, that stuff would sit there in memory and consume that 64 gigabyte of memory and never free it up for anything. So that's why they got to bring swapping back into Irix again as part of a Miser implementation. Anyway. So swapper is a special system thread. It really has no meaning on Irix. It's got a lot more meaning in Unicos and standard Unix machines. The swapper is basically the parent of all processes. It starts off at a PID of 0 and then forks off init, the inetd, and all the processes to get your login environment working. And SCED is the first thing on the system. And they've done a sar-p here now. Sar-p is describing what's happening with my paging on my system. It is a very useful number. In this example, the first column here is vfaults. That's Tlb misses. These are exceptions to the kernel to say, please find this page for me. It's called a validity fault. And then that validity fault is broken into 1, 2, 3, 4 different pieces. Dfill says the page did not exist yet and I have to create it for the first time. Demand fill. So I demand the page, it did not exist. I then have to allocate it and actually initialize it, zero it out or something. The demand fills do take the block transfer engine. There have been a couple of Irixes where you can turn that off with systune. But in general, that is one way of tying up the system on an origin system, because now this interconnect topology is busy creating pages. And if I fire off a 64 gigabyte process, pretty soon my interconnect, the router technology, is busy creating 64 gig of memory, zeroing out these pages, rather than moving data around between the different nodes. So you can really lock out a system pretty bad by overdriving that. It looks like they're coming along and all of a sudden we created a big process that came along and our validity faults shot up significantly, and a lot of them were demand fills and the rest are being satisfied out of file system buffer cache. So vHand is kicking in and stealing, and we can see steals over here. So we're starting to run short of memory. vHand says that, starts stealing pages from the validity faults or the demand fills and then pushes them into cache. And then when I re-reference the page, it's being satisfied out of cache. Okay. And then the page to swaps, this is to the actual swap device. None of my pages are being satisfied out of swap. So even though I've oversubscribed memory, I haven't actually overflowed to the swap device yet. It's when that one kicks up that you start worrying. What does bother me in this one, though, is page files. This is pages for text portions of the program, where I've run short of memory, I've released it, but now within my shell I have to jump back to a text portion that isn't there anymore. Now I have to go to the file system and get that. And this would definitely be affecting the interactive environment, as all my executables have to pull in text pages to run. Of interest to me would be a limit called Rss Current. We'll take a look at some of these limits. But if Rss Current is too small, I'm going to start stealing pages non-discriminately from everything, and then I'm going to have to go off to my file system to get the executable portion of my program every time I hit a page that's not in memory.